Welcome. In math and physics, we often run into these beautiful, intricate structures, like the Feigenbaum singularity, that seem to just evaporate when we change the rules a little bit. Now, previous work in the non-holomorphic fractal series showed this happening on a computer. But that brings up a really big question. Is the singularity just hiding somewhere we can't see it, or is it truly, provably gone? Well, paper 29, in just a few elegant pages, answers that with a pretty definitive yes.
Okay, so let's really frame the core challenge here. The earlier papers in this series gave us some really compelling numerical evidence. The data was basically screaming that the classic Feigenbaum singularity vanishes the moment you introduce a non-holomorphic term. But here's the thing about numerical methods, right? No matter how precise they are, they can only tell you what is happening in your simulation. They can't tell you what must be happening universally. So the fundamental question paper 29 tackles is this: can we build a formal analytic argument that proves a singularity isn't just absent, but that it's analytically impossible at that point?
So here's how we're going to walk through the paper's logic. First, we'll look at that initial observation, the vanishing singularity. Then we'll unpack the three key theoretical ingredients that are used to build the actual proof. After that, we'll look at the main theorem itself, see how it holds up against some numerical checks, and then, finally, we'll close the loop and see how this paper really serves as the capstone for this whole line of research.
All right, so let's start by framing the core problem. This whole area of research didn't begin with a theorem. It actually started with a really surprising observation from computer simulations, an outcome so consistent and startling that it even got its own name.
And that name was outcome B. Using a powerful numerical tool called Pade approximants, which are great for sniffing out singularities from a power series, researchers saw that the Feigenbaum pole didn't just move, it seemed to disappear entirely. But you have to remember, a Pade approximate is basically a very, very sophisticated form of curve fitting. It gives you strong evidence for sure, but it isn't a formal analytic proof. The door was still wide open for a more fundamental explanation, one based on the actual structure of the equations.
So, to build that formal proof, paper 29 doesn't just invent a bunch of new math out of thin air. No, its real genius is in how it synthesizes three critical, interlocking results from the three papers that came right before it in the series.
You can think of these as the three essential tools for the job. Paper 26 gave us a key structural identity. Paper 27 provided a sort of coarse but absolutely crucial bound. And then, paper 28 came along and sharpened that bound to make it truly powerful. You need all three of them working together.
The decoupling lemma. This is a brilliant piece of simplification. It takes the incredibly complicated two-dimensional dynamics of the system and shows that when all you care about is how fast the coefficients are growing, it behaves almost exactly like a much, much simpler one-dimensional chaotic system. That's a huge leap, right? It basically turns a really hard problem in complex analysis into a more manageable one in ergodic theory, the study of the statistical properties of these kinds of systems.
So once the problem was reframed in the language of ergodic theory, paper 27 brought in a classic tool from probability theory, the law of the iterated logarithm, or LIL for short. This law puts a very strict speed limit on the fluctuations of that ergodic sum, and the result was a proof that the coefficients have what's called a finite exponential type. All that means is that their growth rate is controlled. It's bounded by an exponential function, so they can't just grow pathologically fast and run away from you.
Now, that first bound from paper 27 was a huge first step, but it just wasn't precise enough to draw a final conclusion. So, paper 28 did the really meticulous work of refining the constant inside that LUB bound, making it incredibly sharp. We're talking almost 800 times tighter, and that level of precision is exactly what was needed to go from a general statement to a specific, really powerful result.
Okay, so now we have our three key ingredients: the decoupling, the LAL gate, and that super sharp constant. Let's see how they all get combined to forge the main theorem of paper 29.
And here it is, Theorem 2.1. This is the formal statement. What it says is, if you assume something pretty reasonable about the system's chaotic mixing, then the growth rate of the Borel coefficients is ultimately bounded by some finite number, which we call rho of epsilon. This is the mathematical proof that a finite exponential type exists.
And the logic of the proof is just so elegant. Step 1, you use the decoupling lemma. Step 2, you split that sum into its average growth and its random-looking fluctuations. Step 3, this is crucial, you use that sharp LIL constant to show the fluctuations are sublinear. They grow slower than n, and that means, in the long run, only the average growth actually matters. So for step 4, that average growth rate is what defines our exponential type, rho of epsilon. The direct consequence of this theorem is really powerful. There's a standard tool in complex analysis called the root test, and it connects the growth rate of a series coefficients to its radius of convergence. So since we just proved the growth rate is bounded by rho of epsilon, the root test guarantees that the corresponding Borel transform function has to be analytic. That means smooth, no singularities, inside a disk of radius 1 over rho of epsilon. The big question then becomes, how big is that disk?
And this right here is the absolute critical distinction at the heart of the paper. What is proven is the existence of this finite growth rate, rho. The theorem guarantees a disk of analyticity exists, period. But what the theorem doesn't do is calculate the size of that disk. To find out if that disk actually covers the Feigenbaum point, you have to go back to the computer and calibrate its value. That calibration gives you a value of about 0.0942. And since the inverse of that is way bigger than the location of the Feigenbaum point, well, the theorem guarantees the point is safely inside that smooth analytic region.
So with the analytic proof locked in, the paper then goes back to those numerical Pade methods. But this time, it's not looking for evidence of a new discovery, it's using them as a way to confirm that the predictions of the theorem actually hold up in practice.
Just look at this table. When epsilon is 0, that's the pure homomorphic case, you've got a pole right at the Feigenbaum point, and the coefficient growth rate is massive, around 141. But for any non-zero epsilon, even one as tiny as 10 to the minus 10, two things happen instantly. The nearest pole jumps way out to a stable distance of about 105, and the growth rate just collapses to that small value of around 0.0942 that we just talked about. It's a night and day difference.
And this stable distance of about 105 is exactly what you would expect to see if the Feigenbaum point were now sitting deep inside a smooth analytic region. The Pade approximate is hunting for a singularity, but because the function is now proven to be smooth there, the closest one it can find is very far away. Now this specific number, 105, depends on the numerical resolution, but its stability across all these different epsilon values is really strong confirmation of the theorem's prediction.
And I'm going to say it one more time because this is really the intellectual core of the paper. These numbers are a sanity check. They line up perfectly with the theory. But the proof is the analytic argument we just walked through, not the output of the Pade engine. This is confirmation, not proof.
Okay, so let's zoom out one last time. This paper isn't just some isolated result. It's really the culmination of a multi-year research program. So let's place this achievement in that bigger picture.
This timeline just captures the scientific process so beautifully, doesn't it? It starts with an observation made with numerical tools. Then comes a conceptual explanation with the decoupling lemma. That's followed by quantification using the LIL bounds. And then finally, paper 29 comes in and provides the rigorous proof, closing the entire analytic loop.
So what's the big takeaway here? Paper 29 completes the journey. The idea that breaking holomorphy destroys the Feigenbaum singularity is no longer just a compelling hunch from a computer, it is now a direct consequence of a theorem. The singularity is analytically excluded, not just numerically absent.
But you know, science is never really finished, and the paper is very upfront about its foundations. The entire proof rests on something called hypothesis A, an assumption that the underlying chaotic system mixes exponentially fast. Now this has been validated up and down with numerical tests, but a formal proof from first principles? That remains an open problem. And that right there is the next frontier for this work.